Hello and welcome back to Statistics1. We are continuing our chapter 3. This is a section 2 on measures of variation. So we had that example earlier with houses, and we said that when all of the houses were roughly $300,000 each, the mean and the median were pretty much the same number, and we said there was no variation in that data. We didn't talk about variation of the data, but we see that, you know, if each house is roughly 300,000, common sense tells us there is no variation. Until that one person won a lottery and then decided to build a castle in a neighborhood rather than moving out. Well, now the $300,000 house is replaced by the $5 million house, and we saw that the median, while median stayed the same, the mean changed drastically, right? And it went $500,000 up, actually. So that was a lot. From 300,000 to 820 or something like that. So now we would like to take a look at variation in data, because it is important to us to understand those situations when the data varies and when, you know, not all of the entries are, you know, around mean and median and so on. So the first one is range. This would be the first measure of variation, and simply goes in organized data set. Every time I say organized data set, that means you have the smallest to largest value. Range in organized data set, 2 dots, there we go. Range equals max minus the min. Very simple. So find the highest entry, find the lowest data entry, right, and just subtract them. So it's very, very simple. They give this example with the basketball teams. I like this example because it does show variation nicely. You have a basketball, so you have 2 basketball teams. One has heights of, and we know height is very important for basketball. So 72, 73, 76, 76, and 78. On the other team, we have 67, 72, 76, and then 76 and 84. So now, if you consider range for the first one, 78 minus 72 is 6 inches. But if you consider range for the second team, the green team, we have 84 minus 67, which is 14-inch range. Not 14, 17. I was testing you and you just said nothing. So we see that the first team, look at all of the heights. Right? They're within 6 inches. All of the heights are within 6 inches from each other. So pretty much all of the members of this team are the same height, right, within 6 inches, where the other team has a 67 and 84, and they are 17 inch apart, right? So that's a lot of variation in height in that one. So we can see that from the range. So, as I said, max value minus min value, right? That's your formula. This is something that you would do for your project. The three formulas from previous lecture, median, mode, and mean, you do that for your data, for the project data. Now you have this range. And now we have sample standard deviation. If there's one calculation you will be sick by the end of the course, is this one. It's going to show up everywhere, and it shows the variation of data. Standard deviation is present in all of the statistical analysis, and it's something that you calculate to create the ranges, like classes in which the data points are going to fall into. So the higher the deviation, the more variation in data, and the lower the standard deviation, less variation in data. So let's write that first. So the higher standard deviation, the more variation. And then the opposite, obviously, the less standard deviation, the less variation. So now we go and we write the formula. So the formula is, lock the doors, lowercase s is equal to square root, should be large, because we have a fraction inside, which is a summation of, and now we have our xi minus x bar squared divided by n minus 1 in denominator. This is the formula that we will be using. Put some barbed wire or something around it. Make sure it doesn't escape your notebooks. And we can calculate standard deviation for the basketball team we had earlier. And we can calculate, let's calculate for the one that had more variation, that had a range of 17. So we'll go and compute that data set. Now, the way to deal with this is to create a chart. That's the fastest way to, and just use the order of operations on top. So we have our X entries. Those are the actual heights. 67, 72, that's 27. 72, 76, another 76, and 48. Thank you for paying attention. I was just testing. I keep testing. That's really good. Now, if you carefully observe your chart, you all see x bar, right? We know that x bar is a mean. So we actually have to calculate the mean. So let's just add all of these data values. So sum of all the data values. What do we have? 10, 23, 25, and then that's 10, 24, 31, 37. 375? And now x bar is going to be 375 divided by 5, because we have 5 entries. So that's going to be 75. So now let's take a look at our formula. The first are our, you can put this as xi, right? xi, x1, x2, x3, x4, x5. So we have those xi's. Those are our original values. Now if you look over here in the formula, you have order of operations, PEMDAS, and if you have the order of operations, you have to follow order of operations to, so PEMDAS, order of operation, parentheses first, then you have exponents, then you have multiplication, division, whatever is first, and then you have addition and subtraction, whatever is first, right? So M and D are of the same weight category. So it's not multiplication before division. Sometimes it's division before multiplication. Depends on what's first to the left when you are working on the problem. So now, when you look at this, we have parentheses. So we have to work on xi minus x bar first. And that's simply 67 minus 75, 72 minus 75, 76 minus 75, another 76 minus 75, and finally 84 minus 75. So the numbers are negative 12, negative 3, positive 1, and 9. So we have our values. We are only interested, obviously, in those results. And this is our xi minus x bar squared. So we are now squaring these to get 144, 911, and 81. So all I did is I squared all of the values. Now, what's negative? Oh, yes. Negative 8, so that's a 64. I looked at it wrong. Well, thank you. I was testing you and you just passed. So now, the next thing in the formula, we need to add all of those values. We can just add them here. So summation, add everything. So we have, that's 75, right? 74, 75, 76, 156. So where are we now in our formula? We are at S equals square root of 156 divided by 4. That's where we are. Remember that this is the 4 is the 5 minus 1, right? And now all we need to do is to compute this. The denominator is n minus 1. We have 5 basketball players, so n is equal to 5, right? So 5 players means n is equal to 5. The formula says n minus 1. Oops. N minus 1 is 5 minus 1, which is 4, and that goes in the formula. So now S equals square root of 156 divided by 4. And finally, square root of 39 is 6.24. 6.2, whatever. So we came up with a standard deviation of 6.24. And now what it does, it creates the cutoff points for first, second, third standard deviation. So we'll be clearly looking at that much more closely. We'll just see if we are actually interpreting this stuff here. Yeah, we are. So now, this is known as sample standard deviation. We are going to have a population one, and it's going to have a different formula. So please be careful. And first learn this one, obviously. So now we have a sample standard deviation. And what I can do is I can partition my x values, right? Mean is 75, so that goes in the middle. And then we're going to have 3 standard deviations to the right and 3 standard deviations to the left. So this way we're going to add 624. So when I add this, it's going to be 81.24. Then I add another one of these, so that's going to be 87.48. And I'm going to add this again for 93.72. So these are 3 standard deviations to the right. So these are 3 standard deviations to the right. And now we're going to subtract these values. So minus 6, that's going to be 68.76. Then subtract again for 62.52. And subtract again minus 6. So it's going to be 56.28, right? 28. And these are 3 standard deviations to the left. So now, if you take a look at your observations, you can do the dot plot. What do we have in terms of the height of these basketball players from before? Well, you look at the data. We have 67. 67 is somewhere over here. Then we have 72. 72 is somewhere over here. Then we have 2 76s. And we have another one at 84. So these are the 5 basketball players on a dot plot. And we see that they're pretty much all within 2 standard deviations to the left and to the right. Right? You have, so this 75, which is your mean, 75, which is the mean, I'll make it larger. And then we have, I'll draw light, these barriers for 1, 2, 3 standard deviations to the left and to the right. So you can see that there's 2 standard deviations over here to the left, at 2 players, and 2 standard deviations to the right. We're going to have also some rules. 3 standard deviation rule. Almost all the observations in any data set lie within 3 standard deviations to the either side of the mean. So the late Stephen Hawking, his IQ was out of the 3 standard deviations. So we measured the IQ test. We talked about IQ test on a day 1, right? When I said if you want to know if you're smart and stupid, look at the IQ test, not at the math exam, because we don't test for IQ. You have, on the IQ scale, you have 100 to be the mean, and then you're adding 15 and subtracting 15 or 16, depending on which school of thought you take. It's 15 or 16. So we have 115, 130, and 145 for the 3 standard deviations to the right. And then you have 85 and 70 and 55 on the left. So what we have is the average on 100. We have what in psychology is known as retardation, right? Which is 80, I think 83 and less. Military is not hiring under 83 IQ. There are no jobs that military can provide, and usually that is the one employer who will take anyone, right? Because they need everyone they can get. So if they put their cap at the lowest of 83, then right, the rest is unemployable by that. And that's actually 16% of any nation is less than 83. So a sixth of a population is unemployable, which lives off of the Social Security for their entire life. Yeah. But you have the other end, right? You have the other end of the spectrum where Stephen Hawking was clocked at 160. That's 4 standard deviations to the right in terms of the standard IQ intelligence. So if you want to know where you are on this scale, right? If you want to know where you're on this scale, you would actually have to take the test. And it's expensive. I think it's like $200 or $400 to take the IQ test. But you have the ones that are free on the internet, and they're not, perfect, but they would be in the neighborhood of where you actually are, and you can read. So we'll continue. The lecture is over. All of the theory. I just don't like that I only did one example. So next class we are not going to stream this examples. We're going to do 2 or 3 examples of standard deviation, and then we'll go with the next lecture. Bye. So we'll do IQ more.